A mysterious radio signal once screamed from deep space, and we have never heard it again. The universe is not a simple puzzle to be solved, but a conversation where every answer sparks a flood of new questions. We are about to journey through 30 of the cosmos's most profound discoveries, each one a revelation that left experts more perplexed than before. From stars that vanish without warning to an invisible force tearing reality apart, these are the enigmas that define the frontiers of our knowledge. By the end, you will see the universe not as a static map, but as a living, breathing mystery that constantly rewrites its own rules. We will encounter signals that hint at other minds and forces that dictate the fate of everything. What do you believe is waiting for us in the cosmic dark? The first great cosmic question arrived not with a whisper but a scream. On the evening of August 15, 1977, an astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was methodically scanning the sky for any unusual radio signals, a routine part of the search for extraterrestrial intelligence. As Amon pored over the printed charts, his eyes locked onto a column of letters and numbers. One sequence stood out so dramatically that he circled it in red pen and in the margin wrote a single powerful word: "Wow." The signal was a pure, narrowband radio burst at exactly the frequency hydrogen atoms emit in the quiet of space, a logical channel for any civilization trying to be heard. It lasted for a full 72 seconds, the exact time it took for the Big Ear's field of view to pass over that point in the constellation Sagittarius. It came from nowhere and then it was gone. In every way that mattered, it looked artificial. It was the kind of signal astronomers had hoped to find for decades. And then nothing. Despite countless follow-up searches by telescopes around the world, the WOW signal never repeated. It became a ghost in the machine, a one-time cosmic event that left an indelible mark. Was it a natural phenomenon we simply do not understand, like a previously unknown type of stellar flare? Could it have been a reflection of a human-made satellite, bouncing off space debris in a perfect, unrepeatable alignment? Or was it, as many still hope, a fleeting message, a cosmic hello that we heard only once because we were listening at just the right moment? This single event, a scribbled word on a printout, fundamentally reshaped the search for extraterrestrial intelligence. It taught scientists a frustrating lesson that a perfect candidate signal is meaningless if it cannot be verified. It fueled debates that rage to this day about how we interpret such detections and forced the development of new protocols. The WOW signal did not answer the question of whether we are alone. Instead, it made the silence that followed somehow louder and the vastness of space feel infinitely more mysterious. That profound silence after the WOW signal taught astronomers to look for more than just messages. They learned to search for shadows. Years later, a new kind of mystery would emerge not from a radio telescope's data, but from the keen eyes of citizen scientists sifting through star charts from the Kepler Space Telescope. They found a star in the constellation Cygnus, officially named KIC 8462852, but known to the world now as Tabby's star. At first glance, it seemed ordinary, a sun slightly larger and hotter than our own, sitting over 1,000 light-years away. But its light told a different story, a tale of something strange passing in front of it. Kepler was designed to find planets by spotting the tiny, regular dips in starlight caused by an orbiting world. A planet like Jupiter would block about 1% of a sun's light. The data from Tabby's star showed something incomprehensible. The star's brightness would plummet by enormous amounts, up to 22%, and these dips were not neat and periodic. They were chaotic, irregular, and deeply asymmetric, as if vast, jagged shapes were drifting haphazardly through space between us and the star. No natural planet, not even a gas giant, could create such a dramatic shadow. Theories rushed in to explain the impossible. The first and most conservative idea was a colossal swarm of comets, thousands upon thousands of them, breaking apart and casting their dusty debris into a complex, clumpy cloud. But to dim the star, that much would require an almost unimaginable number of comets, a scale of destruction that seems statistically bizarre. Then came a more provocative suggestion, one that leaped from the pages of science fiction into serious scientific discourse. What if we were seeing a Dyson sphere, or at least the beginnings of one? This is a hypothetical megastructure, a concept from futurist Freeman Dyson, where an advanced civilization would surround its star with a vast array of energy-collecting satellites or platforms to harness nearly all of its power. A partially built or fragmented Dyson sphere with its uneven panels and open frames could perfectly explain the strange, irregular dimming patterns. This idea places the potential builders as a Type II civilization on the Kardashev scale, a society that has mastered the energy output of its entire star system. Tabby's star forces us to confront a fundamental question about our search for intelligence beyond Earth. For decades, we listened for deliberate signals, for a cosmic phone call. But what if advanced civilizations do not bother calling? What if they simply build on such an epic scale that their engineering projects become visible across the galaxy as anomalies in the light of their stars? This star challenges our methods at the deepest level, blurring the line between astrophysics and archaeology. Are we looking at a natural astrophysical process so rare we have never seen it before, a cosmic teenager going through a dusty phase we do not understand? Or are we, for the first time, staring at the silhouette of a project so vast it defies human comprehension? The star keeps its secrets flickering unpredictably, a riddle written in missing light that asks us to reconsider what evidence of other minds might actually look like. The search for cosmic shadows and alien megastructures deals with the immense, but sometimes the deepest mysteries are hidden in the smallest details. As our robotic envoys, the Pioneer 10 and Pioneer 11 spacecraft, completed their grand tours of the outer planets and began their eternal journeys into interstellar space, they carried with them a secret. Mission controllers, tracking their positions with exquisite precision using radio signals, noticed something was off. Both spacecraft, billions of miles from the Sun and coasting under pure inertia, were slowing down just a tiny bit more than they should have been. An unknown force was acting upon them, an almost imperceptible but constant deceleration pulling them back toward the inner solar system. It was minuscule, a deviation so small it was like measuring the width of a human hair from a distance of 1,000 miles, but it was undeniably there. This was the Pioneer anomaly. For decades, this tiny tug-of-war confounded physicists. The deceleration was too small to be explained by the gravitational pull of known planets or the Kuiper belt. It was too constant to be random. It suggested that either our understanding of gravity itself was subtly incorrect in the vast, cold emptiness between stars, or that some unseen, diffuse force was at work. Theories flourished, some suggesting the gravitational influence of dark matter, others proposing modifications to Einstein's theory of general relativity, like modified Newtonian dynamics, which attempts to explain galactic rotations without dark matter. The Pioneer anomaly became a symbol of a potential crack in the foundation of physics, a hint that the rules governing the cosmos might change in the profound quiet of deep space. The mystery's resolution came not from exotic new physics, but from painstaking detective work on the spacecraft themselves. The leading explanation points to something remarkably mundane: thermal radiation. The spacecraft were powered by radioactive plutonium, and the heat from that power source, radiating unevenly off the craft's structure and antenna dish, acted like a tiny, gentle thruster pushing back toward the sun. It was the spacecraft's own warmth slowly bleeding into the void that created the phantom deceleration. Case closed then, a triumph of meticulous analysis. But the legacy of the Pioneer anomaly is far more profound than its solution. It raised a critical, practical question for our future. If we ever hope to send probes or even one day ships to other stars, we must be able to predict their trajectories with absolute precision over centuries. A minuscule, unaccounted for acceleration, whether from thermal radiation, the subtle pressure of sunlight, or even interstellar dust, could mean missing a target star system by trillions of miles. The anomaly taught us that interstellar navigation is not just about having a powerful engine. It is about accounting for every single whisper of force, no matter how small. It proved that the emptiness of space is not truly empty, and that to travel through it, we must understand the physics of everything, right down to the last photon of heat radiating from our own vessels. This tiny puzzle, solved with earthly engineering, ultimately points to a universe of exquisite subtlety, where our greatest journeys will be guided by our mastery of the most minute details. The Pioneer probes taught us to measure every whisper of force, but what happens when the universe itself whispers with a gravity that has no visible source? This is the heart of the fourth great cosmic discovery, a substance so elusive we have never seen it, touched it, or created it in a lab. We only know it must be there because the cosmos would literally fly apart without it. We call it dark matter, and it constitutes roughly 27% of everything that exists. You, me, every planet, every star, every galaxy we see with our telescopes, all of that normal matter accounts for less than 5% of the universe. Dark matter is the invisible scaffolding upon which the visible universe is built. The first compelling clue came from the way galaxies spin. According to the laws of gravity, stars on the outer edges of a spiral galaxy, like our own Milky Way, should orbit much more slowly than those near the dense center. Think of our solar system, where distant Pluto crawls along its orbit compared to speedy Mercury. But when astronomers measured the rotation speeds of galaxies, they found something shocking. Stars on the outskirts were whipping around just as fast as those near the core. The visible mass of the galaxy, all its stars and gas, simply did not provide enough gravity to hold these speeding outer stars in place. The only explanation was a massive, invisible halo of something enveloping the galaxy, providing the extra gravitational glue. The second line of evidence is even more dramatic, a phenomenon called gravitational lensing. Einstein predicted that massive objects warp the fabric of space-time, bending the path of light like a lens. When astronomers look at massive galaxy clusters, they see distant galaxies behind them stretched and distorted into faint arcs and rings. The amount of bending is far greater than the visible mass of the cluster can produce. An enormous amount of unseen mass, dark matter, must be there, warping space like a hidden lens. Finally, the faint afterglow of the Big Bang, the cosmic microwave background, bears the imprint of dark matter's gravity from the universe's infancy, influencing how the first structures formed. So we know it is there, and we know it is everywhere, but what is it made of? That is the monumental question. The leading candidate for decades has been a theoretical particle called a WIMP, a weakly interacting massive particle. As the name suggests, these particles would have mass and interact through gravity and possibly the weak nuclear force, but otherwise ignore normal matter, passing right through our planet and our bodies as if we were ghosts. To catch one, scientists have built exquisitely sensitive detectors deep underground in abandoned mines and beneath mountains, shielded from cosmic rays. These experiments wait for the incredibly rare moment a dark matter particle might bump into an atomic nucleus. So far, after years of searching, the detectors have remained silent. Another candidate is the Action, an ultra-lightweight particle conceived to solve a different puzzle in particle physics. These would behave more like a pervasive, wavering field than a discrete bullet. The null results are not failures, they are guideposts telling us where dark matter is not, narrowing the search. This leads to a profound lifestyle implication that stretches the imagination. If dark matter is a sea of particles flowing through us and everything around us, what if we could one day perceive it or even interact with it? Harnessing it sounds like the realm of fantasy, but consider the possibilities. Could a dark matter engine provide a new form of propulsion, using the gravitational influence of this invisible substrate to maneuver through space in ways we cannot yet conceive? Might it offer a lens into entirely new states of energy or dimensions we are currently blind to? Understanding dark matter would not just fill a gap in our cosmic ledger, it would revolutionize our conception of reality itself, revealing that most of the universe's substance operates on a hidden channel, a silent partner in the dance of the cosmos that we have only just begun to hear. If dark matter is the invisible scaffolding holding galaxies together, then dark energy is the phantom force tearing the fabric of the cosmos apart. It is an even deeper mystery, a form of energy inherent to empty space itself that causes the universe's expansion to accelerate. This discovery, one of the most shocking of the 20th century, completely overturned our cosmic forecast. For decades, astronomers believed the universe's expansion, following the Big Bang, was gradually slowing down due to the collective gravitational pull of all matter. The ultimate question was whether that pull would be strong enough to one day reverse the expansion in a big crunch, or if the universe would coast forever into a cold, dark fade. In the late 1990s, two independent teams set out to measure this deceleration by observing a specific kind of stellar explosion called a Type I, a supernova. These supernovae are cosmic standard candles. They always explode with nearly the same intrinsic brightness. By measuring how dim they appear from Earth, scientists can calculate their distance with great accuracy. By also measuring how much their light is stretched or redshifted by the expansion of the universe, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were not just surprising, they were paradigm-shattering. The distant, ancient supernovae were fainter than expected. This meant they were farther away than our models predicted, which in turn meant the universe was not slowing down at all. It was speeding up. Some unknown repulsive force was overpowering gravity on the largest scales, pushing galaxies apart at an ever-increasing rate. This force was dubbed dark energy, and it constitutes a staggering 68% of the total energy and matter in the universe. Think of it this way: for every one particle of the normal matter that makes up stars and planets, there are about 5 particles of dark matter holding galaxies together, and about 14 units of dark energy working to push everything apart. The leading explanation for dark energy is Einstein's old idea, the cosmological constant. He originally introduced it as a fudge factor to keep the universe static in his equations, later calling it his greatest blunder. But in this new context, it represents a constant energy density filling the vacuum of space, a property of empty space itself that generates a repulsive gravity. If this is true, dark energy is simply how space behaves, a fixed feature of reality. Another possibility is that dark energy is not constant, but a dynamic field that changes over time, known as quintessence. This would mean the strength of this repulsive force could vary, leading to different possible futures. The most unsettling possibility is that dark energy is not a new substance at all, but a sign that our theory of gravity, Einstein's magnificent general relativity, breaks down on the scale of the entire observable universe. This forces us to confront the ultimate fate of everything. If dark energy remains constant as the cosmological constant suggests, the acceleration will continue steadily. Galaxies outside our local group will eventually be pushed so far away their light can never reach us, leaving our descendants in an island universe surrounded by an ever-darkening void, a fate called the Big Freeze or heat death. If dark energy as quintessence grows stronger over time, it could eventually overcome all forces, tearing apart galaxies, then solar systems, then planets, and finally atoms themselves in a catastrophic Big Rip. The remote chance of a big crunch now seems all but impossible. Understanding dark energy is not an abstract exercise. It is the key to predicting the cosmic destiny of any civilization that hopes to endure. Will the universe provide an infinite, if lonely, theater for future generations? Or does the vacuum of space itself contain the seeds of a final, inescapable dissolution? Dark energy asks us the most profound question of all, not about how the universe began, but about how it will end and whether anything we ever build can truly last. While dark energy dictates the universe's ultimate fate, deep within the cosmic static another kind of signal arrives, a brief scream of energy so powerful it defies belief. These are fast radio bursts, or FRBs. Imagine the entire energy output of our Sun, not over its 10 billion-year lifetime, but compressed into a single, brilliant millisecond. That is the staggering power of an FRB. These are not the long, drawn-out signals of the wow discovery, but cosmic firecrackers, sudden and intense flashes of radio waves that travel across billions of light-years only to vanish almost as soon as they appear. The first was identified in 2007, hidden in old data from a radio telescope in Australia. Since then, we have detected hundreds of them, each one a pinpoint eruption in a distant galaxy. The mystery deepens with a crucial split in the data. Most FRBs are one-off events, a single, catastrophic flash from a source that then goes permanently dark. But a precious few are repeaters. They fire off again and again, sometimes in predictable patterns, sometimes erratically, like a cosmic lighthouse with a faulty switch. This simple fact that some repeat and some do not suggests at least two different kinds of cosmic engines are at work. So what could possibly create such a titanic, fleeting burst? The leading candidate is a type of stellar corpse called a magnetar. A magnetar is a neutron star with a magnetic field so strong it could wipe a credit card clean from halfway across the solar system. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its insane magnetic field, could snap like a cosmic rubber band, releasing that colossal energy in a radio flash. This fits the one-off bursts well, a single cataclysmic event. For the repeaters, we might be looking at a magnetar orbiting in a dense cloud of debris, with each pass through the cloud triggering a new eruption. Yet the extreme energy pushes the limits of even these monstrous objects, leaving room for more exotic ideas. Some physicists have proposed cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang, snapping and vibrating. Others, far more speculatively, have wondered if we are seeing the side effects of technology. A beam of energy powerful enough to push a light sail on an interstellar spacecraft, if it happened to sweep across our line of sight, would look exactly like an FRB. While this is not the leading explanation, its mere consideration highlights how extraordinary these signals truly are. Beyond their origin, FRBs are becoming unexpected tools. As these radio waves race across the universe, they pass through the diffuse clouds of gas and dust that float between galaxies, the universe's missing baryonic matter. The burst's different frequencies get slightly scattered by this material, and by measuring that dispersion, astronomers can literally weigh the invisible stuff between galaxies. Each FRB is a flashbulb illuminating the cosmic web, allowing us to map the universe's hidden architecture, so we are left with two profound puzzles. First, what natural process or processes can act as a universe-spanning flashgun, concentrating more energy than we can fathom into a blink that outshines entire galaxies? And second, if some of these sources are repeating, what is the stable, reloading mechanism that allows for such serial explosions? Each new detection is not an answer, but a sharper question, a reminder that the cosmos is still capable of producing phenomena that, for a glorious millisecond, outshine everything we think we know. The universe's millisecond fireworks are fleeting, but in 2017 we were handed a cosmic artifact to hold in our gaze, if only for a moment. That October, a telescope in Hawaii spotted a faint point of light moving at blistering speed. Its path was hyperbolic, meaning it was not bound to our sun, it was just passing through. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. It was the first confirmed object from another star system to visit our own. As telescopes around the world swiveled to track it, the data revealed a shape unlike anything in our solar system. It was not round. Measurements of its brightness, which varied dramatically as it tumbled, suggested an extreme, elongated form, perhaps 10 times as long as it was wide, like a cosmic cigar or a rocky pancake tumbling end over end. This alone was peculiar, but the real mystery came as it began to depart. As Oumuamua sped away from the sun, something was giving it an extra push. Its trajectory could not be explained by gravity alone. It exhibited a small but clear non-gravitational acceleration. For a comet, this is normal. The sun's heat vaporizes ice on its surface, creating jets of gas that act like tiny thrusters. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that surrounds a comet's nucleus. It looked utterly inert, a dark, silent rock, yet something was propelling it. The scientific debate ignited. One camp argued it was a very unusual comet after all, one with a surface crust so thick that any escaping gas came from cracks in just the right way to produce the acceleration without a visible dust cloud. Perhaps it was a dust-rich object where the sun's radiation pressure on fine particles provided the push. Another, more recent theory proposed it was a chunk of frozen nitrogen, sheared off from a Pluto-like world in another system. As it neared our sun, the nitrogen ice would have sublimated, providing the thrust and explaining the pancake-like shape as layers eroded away. Then there was the more speculative possibility. Its shape and acceleration profile reminded some scientists of a light sail, a thin, reflective sheet pushed by starlight. Could Oumuamua be a piece of discarded technology, a broken solar sail from a long-dead civilization, drifting between the stars? While most astronomers strongly favor a natural origin, the very fact that the artificial hypothesis was seriously discussed in scientific papers speaks volumes about how strange this object truly was. Oumuamua's lasting legacy is not a definitive answer, but a profound shift in perspective. It proved interstellar visitors are real and likely common. Our solar system is not a closed ecosystem. We are continually swept by debris from other stellar nurseries. This has spurred ambitious new mission concepts like the European Space Agency's Comet Interceptor, designed to wait in space for the next Oumuamua and race out to meet it. We missed our chance with the first scout, but its brief passage taught us to be ready. The next time an interstellar messenger arrives, we intend to get a much closer look, to finally read the inscription on a letter from another star. Oumuamua's passage proved we are not alone in a cosmic neighborhood sense, but its silent journey only deepens a far older and more profound puzzle. Decades ago, physicist Enrico Fermi posed a simple, devastating question over lunch with colleagues. Given the sheer age and size of the universe, with its hundreds of billions of stars and planets, where are all the aliens? If life and intelligence are common, the galaxy should be teeming with civilizations. Their ships, or at least their signals, should be everywhere. The silence we encounter, the great silence as it is sometimes called, is the core of the Fermi paradox. It is the stark contradiction between high probability and empty observation. The multitude of solutions proposed are not just scientific guesses, they are mirrors reflecting our own hopes and fears about the universe. One of the most sobering is the concept of the Great Filter. This idea suggests there is at least one nearly insurmountable barrier, a developmental step so difficult that almost all life fails to pass it. The terrifying question is, where is this filter located? Is it behind us, meaning the rise of intelligent, technological life is itself a miraculous fluke, and we have already beaten incredible odds? Or is it ahead of us, waiting to destroy civilizations that reach a certain point? perhaps through self-destruction via war or environmental collapse, or through some unforeseen cosmic catastrophe. Every exoplanet we discover in a habitable zone intensifies this anxiety. If life is common but we see no one, the great filter likely lies in our future. Another class of solutions suggests the aliens are here, but we cannot perceive them. The zoo hypothesis proposes that advanced civilizations are aware of us, but have placed our solar system in a kind of cosmic quarantine, observing us from a distance without interference until we reach a certain maturity. It is a galactic prime directive, the dark forest theory, drawn from science fiction but taken seriously in these discussions, paints a far grimmer picture. It posits that the universe is like a dark forest where every civilization is a hidden hunter. Broadcasting your location is suicidal because any other civilization you meet could see you as a threat and annihilate you preemptively. In this scenario, silence is not a mystery, it is survival. Everyone is listening, but no one is talking for fear of being hunted. Other ideas are more mundane but equally plausible. Perhaps interstellar travel is simply too slow, too costly, or too pointless for any civilization to undertake on a scale we would notice. Maybe advanced intelligence inevitably turns inward, creating virtual realities so compelling they lose interest in the physical stars. Or perhaps we are simply looking for the wrong things, scanning for radio waves when everyone else has moved on to neutrino communication or something we cannot yet conceive. The Fermi paradox forces us to confront four unsettling possibilities about humanity's place in the cosmos. Are we alone, a rare spark in a vast, empty darkness? Are we first, the earliest civilization to reach this stage in a young galaxy? Are we doomed, destined to be filtered out before we can ever reach the stars? Or are we simply unaware, like ants in a garden, oblivious to the beings walking beside us? How we answer this question shapes everything from our drive to explore space to our philosophy about preserving our own world. It asks what the lifestyle of a truly galactic civilization would even look like, and whether that is a future we are meant to have, or one we must fight against all odds to achieve. The profound silence of the cosmos is broken by a faint, uniform glow, the oldest light in existence. This is the cosmic microwave background, the cooled and stretched afterglow of the Big Bang itself, a snapshot of the universe when it was just 380,000 years old. For the most part, this background radiation is remarkably smooth, a testament to the early universe's uniformity. But within this cosmic wallpaper, astronomers have found a blemish so strange it challenges our entire picture of reality. It is known simply as the cold spot, a vast region in the constellation Eridanus that is significantly colder than the surrounding sky. This isn't a tiny fluctuation. The cold spot spans nearly 1 billion light-years across, a cosmic continent of unexpected chill. In a universe that should be statistically even on such large scales, this anomaly is like finding a continent-sized patch of ocean that is inexplicably cooler than the rest of the sea. The most straightforward explanation is a supervoid, an immense, mostly empty region of space. As light from the cosmic microwave background travels through such a void, it loses a tiny amount of energy climbing out of the gravitational well, a process known as the integrated Sachs-Wolf effect, which would make that region appear slightly colder. The problem is, surveys mapping the galaxies in the direction of the cold spot have not found a void large or empty enough to account for the dramatic temperature drop. The scale just does not match. This mismatch has opened the door to far more speculative and thrilling possibilities. Some cosmologists have proposed that the cold spot could be evidence of a collision with another universe in a vast multiverse. In certain models of eternal inflation, where our universe is one bubble in a frothing sea of other bubble universes, such a collision could leave a distinct imprint on the cosmic microwave background, a kind of cosmic bruise. The cold spot could be the scar from where our nascent universe bumped into a neighbor, an event frozen in the first light. This idea pushes at the very limits of science, as it suggests we might one day gather empirical evidence for realities entirely beyond our own. The implications are staggering. It asks whether the universe is truly homogeneous, or if its largest structures hold fingerprints from events that occurred before the Big Bang as we define it. If the multiverse is real, our entire cosmic history, from the first stars to the rise of life, might be just one narrative in an infinite library of possibilities. The cold spot remains an enigma, a puzzle written in the faintest microwave whisper. Is it a statistical fluke, a rare but natural cosmic underdensity we simply do not fully understand? Or is it a window, a crack in the firmament through which we are glimpsing the architecture of a reality, so vast it makes our own universe seem like a single room in an endless mansion? This cold patch on the sky forces us to question not just the contents of our universe, but its very context. That faint cosmic glow holds the universe's first secrets, but our telescopes now find entire new worlds in the light of nearby stars. In just a few decades, we have gone from wondering if other planets exist to cataloging over 5,000 confirmed exoplanets, with thousands more candidates waiting. This is not science fiction, it is a modern census of the galaxy. Among these, the most tantalizing are those found in the habitable zone, often called the Goldilocks zone. This is the orbital distance from a star where temperatures are just right, not too hot and not too cold for liquid water to pool on a planet's surface. Water, as the essential solvent for life as we know it, makes these worlds the prime candidates in our search for alien biology. Some discoveries feel almost tailor-made for wonder. The TRAPPIST-1 system, a cool red dwarf star about 40 light-years away, hosts 7 rocky planets, and at least 3 of them orbit squarely within that precious zone. Imagine a solar system so compact that all its potentially habitable worlds are closer to their star than Mercury is to our Sun, each appearing as a large neighboring world in the other's sky. Then there is Kepler 452b, a planet dubbed Earth's older cousin. It orbits a sun-like star, has a year 385 days long, and sits comfortably in the habitable zone of a system 6 billion years old, 1.5 billion years older than our own. The data paints a picture of a world that could have continents, oceans, and a long, long history. But this explosion of discovery raises a critical, humbling question. Does a planet being technically habitable mean it is actually inhabited? A world could have all the right conditions and still be a barren desert or a global ocean devoid of life. The real search now shifts from finding these worlds to scrutinizing their atmospheres for biosignatures, the chemical fingerprints of biology. The most promising signatures are gases that should not exist together in a stable atmosphere without something constantly replenishing them. Oxygen, especially in large amounts alongside a gas like methane, is a powerful candidate. On Earth, our oxygen-rich air is almost entirely the product of photosynthesis from plants and microbes. Detecting a similar imbalance on an exoplanet would be the most compelling hint of life we could hope for from light years away, yet the universe is tricky. Every potential biosignature has an abiotic or non-living imposter. Oxygen can be produced in large quantities by the breakdown of water vapor under intense starlight. Methane can seep from volcanic activity or be produced by geochemical reactions in a planet's crust. The grand challenge for the next generation of telescopes, like the James Webb and future giant observatories, will be to untangle this cosmic knot. They will need to measure not just the presence of a gas, but its concentration, its seasonal variations, and the context of the entire planetary system to judge whether a geological process or a living world is the more likely explanation. This search reframes our place in the cosmos. If we find a definitive biosignature, it answers the ancient question of whether life is a cosmic fluke or a common phenomenon. But if we survey hundreds of habitable zone worlds and find them all to be chemically inert, that silence would be equally profound and perhaps more lonely. Looking further ahead, these same catalogues of habitable zone planets become the target lists for humanity's farthest ambitions. Which of these worlds might we one day dream of reaching? A planet like one in the TRAPPIST-1 system, orbiting a stable red dwarf, offers a nearby target, but such stars are prone to violent flares that could strip atmospheres. An older world like Kepler 452b offers stability, but its age means any life there has had a colossal head start. The ultimate lifestyle implication is staggering. We are no longer just stargazers, we are prospectors. We are identifying real estate in the galaxy, weighing the unknowns of alien geology, climate, and potential biospheres we cannot yet comprehend. The challenges are immense, from the sheer distances to the possibility of encountering ecosystems utterly unlike our own, where our very presence might be a contaminant or we might find ourselves vulnerable to alien microbiology. Each new world found in the Goldilocks zone is a dual symbol, a beacon of potential companionship in the void, and a future destination that promises challenges far beyond any we have ever faced. The search for habitable worlds asks what life needs, but a ghostly galaxy in the constellation Cetus asks a far more fundamental question about what holds the universe together. In the vast cosmic dance, dark matter is supposed to be the lead partner, the invisible force that gathers gas and stars into the majestic spirals and ellipticals we see. Then astronomers found a galaxy that seemed to have forgotten the steps. NGC 1052DF2 is an ultra-diffuse galaxy, a faint, wispy collection of stars so spread out you can see right through it. Using the Hubble Space Telescope and the Keck Observatory, scientists measured the motions of 10 glowing globular star clusters orbiting this ghostly galaxy. The speed of those clusters reveals the galaxy's total mass, the gravitational glue holding it all together. The results were stunning. The clusters were moving slowly, lazily, as if there was almost nothing pulling on them. The visible mass of the stars accounted for essentially all the gravity present. There was no room left for dark matter. This was not just a little less than expected, it was a galaxy that appeared to have none at all. The discovery sent shockwaves through cosmology. For decades, dark matter was not just a theory, it was the cornerstone of how we believed all galaxies formed. Its gravitational pull was thought to be the seed around which normal matter could gather and condense into stars. A galaxy without dark matter should not exist according to that model. It would be like finding a towering sandcastle built without any sand, just the shape of it standing defiantly against the tide. So what is going on? One possibility is that this galaxy is a cosmic outlier, a freak of nature with a violent past. Perhaps it was once a normal galaxy rich in dark matter, but it had a catastrophic encounter with a much larger neighbor. In that gravitational tug-of-war, the diffused dark matter halo could have been ripped away, leaving behind the more tightly bound stars as a dark matter-free relic. Another, more radical idea is that our understanding of gravity itself needs revision on certain scales. Theories like modified Newtonian dynamics, or MUND, propose that gravity behaves differently when its pull becomes extremely weak, such as in the outer reaches of galaxies or in these ultra-diffuse systems. In a MUND universe, you would not need dark matter to explain the motions in NGC 1052DF2, because the rules of the game themselves change in its faint gravitational field. The galaxy becomes a test case, a natural laboratory for exotic physics. The most unsettling implication, however, is that dark matter might not be as universal as we assumed. What if it is a substance that can be separated from normal matter under certain conditions? This would mean dark matter is not an inseparable partner to stars, but a component that can be added or removed, changing the fundamental properties of a galaxy. Finding even one such galaxy forces a profound rethink. It challenges us to ask whether our standard model is a complete picture of the cosmos, or if we have been constructing a theory based on the average, while the outliers hold the key to a deeper truth. Is NGC 1052DF2 a bizarre exception that proves the rule, or is it the first clue that the universe builds its structures in more ways than we ever dreamed? While ghostly galaxies challenge our grasp of dark matter, a far more powerful force is pulling on us from the depths of intergalactic space. Our Milky Way, along with its entire local group of galaxies, is not drifting aimlessly. We are all racing toward a specific point in the sky, toward a gravitational monster we cannot directly see. Astronomers call it the Great Attractor. This colossal anomaly lies roughly 250 million light-years away in the direction of the constellations Centaurus and Norma, exerting a pull so immense it dictates the motion of thousands of galaxies across a vast region of space. Our solar system orbits the galactic center, our galaxy moves within the local group, and the entire local group is falling at over 2 million kilometers per hour toward this hidden focal point. The mystery is compounded by its location. The Great Attractor sits directly behind the plane of our own Milky Way, in an area known to astronomers as the zone of avoidance. This is the thick band of stars, gas, and cosmic dust that forms the central disk of our galaxy. It acts like a brilliant, obscuring fog, blocking our optical view of the universe beyond. Trying to see the Great Attractor from Earth is like trying to spot a distant mountain range through the blinding glare and dense smog of a sprawling city. For decades, this zone rendered the attractor effectively invisible, a shadowy presence inferred only by its gravitational tug on everything around us. With optical telescopes blinded, astronomers turn to instruments that can peer through the cosmic fog. Radio, infrared, and X-ray telescopes began to map the hidden landscape. What they found was not a single, unimaginable object, but an immense concentration of mass, likely a gigantic supercluster of galaxies. The leading candidate is known as the Norma cluster, a dense knot of galaxies anchored by a massive elliptical galaxy, all embedded within an even larger web of dark matter. Yet, even when we add up the mass of all the visible galaxies in that region, it still does not fully account for the strength of the pull we feel. There must be even more mass there, hidden behind still more dust or in forms we have not yet mapped. This reveals a humbling truth about our place in the cosmos. We are not stationary observers. We are participants in a grand, flowing river of galaxies, swept along by currents driven by the uneven distribution of matter on the largest scales. The Great Attractor is just one of these colossal nodes in the cosmic web, a gravitational well so deep it bends the paths of galaxies for hundreds of millions of light-years around it. But if it is not the end of our journey, where is it pulling us? Recent observations suggest the Great Attractor itself is moving, pulled toward an even more massive structure billions of light-years away, known as the Shapley supercluster. We are caught in a cascade of gravitational influences, a cosmic hierarchy where clusters attract groups and superclusters attract clusters. This raises profound questions about the architecture of the observable universe. How many other great attractors are out there, hidden behind other galaxies' zones of avoidance? What does this vast, lumpy distribution of matter tell us about the initial conditions of the Big Bang? The Great Attractor forces us to think in 4 dimensions, understanding that the map of the cosmos is not static but a dynamic flow chart, with galaxies tracing the contours of hidden mass like iron filings aligning to a magnet. Our entire local neighborhood is on a billion-year journey toward an unseen destination, reminding us that even the grandest structures we call home are mere passengers in a much larger and still largely uncharted cosmic current. These immense gravitational currents shape the journeys of galaxies, but on a far smaller scale, another kind of traveler streaks across the cosmos with almost impossible power. They are not spaceships but subatomic particles, atomic nuclei stripped of their electrons and hurled across the universe at velocities approaching the speed of light. These are cosmic rays, and a rare few among them carry an energy so staggering it defies our understanding of physics. We call them ultra-high-energy cosmic rays. A single one of these particles, smaller than an atom, can carry the kinetic energy of a professionally thrown baseball, all compressed into a microscopic bullet. This is millions of times more energy than we can produce in our most powerful human-made particle accelerator, the Large Hadron Collider. The mystery is not just their power, but their very existence. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated a fundamental limit for such particles traveling across the universe. They realized that over vast intergalactic distances, these ultra-high-energy protons should interact with the photons of the cosmic microwave background, the faint afterglow of the Big Bang. Each collision would sap a little of the particle's energy, a process that should completely drain them over distances of about 150 million light-years. This is known as the GZK limit, and yet we detect them here on Earth. This presents a cosmic paradox. If these particles cannot travel very far without losing their punch, then their sources must be relatively nearby within our own cosmic neighborhood. But what local astrophysical engine is powerful enough to serve as a natural particle accelerator of such monstrous scale? The prime suspects are some of the most violent objects in the universe. Active galactic nuclei, the supermassive black holes at the centers of galaxies, can spew jets of plasma stretching for thousands of light years, creating shock waves that could potentially accelerate particles to these extremes. Cataclysmic gamma-ray bursts, the death cries of massive stars, could also be candidate factories. Yet, when astronomers trace the incoming paths of these ultra-high-energy rays back into the sky, they rarely point directly to a known, powerful source within the GZK horizon. The particles are charged, so their paths are bent by interstellar and intergalactic magnetic fields, making it like trying to find the origin of a bullet that has ricocheted 1,000 times. To catch these elusive particles, scientists built the Pierre Auger Observatory in Argentina, a detector the size of a small country. It does not catch the particles themselves, which collide with atoms in the upper atmosphere, creating a cascading shower of secondary particles that rain down over several square miles. By detecting this shower with an array of 1,600 water tanks and telescopes watching for faint fluorescence in the night sky, the observatory can reconstruct the original particle's energy and approximate direction. The data is puzzling. The arrival directions of the highest energy events show a weak correlation with the positions of nearby active galaxies, but it is not a perfect match. Some rays seem to come from empty space. This suggests either our catalogue of nearby violent objects is incomplete, or our understanding of how particles lose energy over space is wrong. The latter possibility is the most thrilling. Could ultra-high-energy cosmic rays be messengers of physics beyond the standard model? Perhaps they are not protons at all, but heavier nuclei that interact differently with the background radiation. Or maybe they are the decay products of exotic, super-heavy particles left over from the Big Bang, particles predicted by theories like supersymmetry. Each one that strikes our atmosphere is a probe from the most extreme environments in the cosmos. A tiny, hyper-energetic postcard that reads, "Figure this out." They force us to ask whether the universe contains natural accelerators of a ferocity we have not yet imagined, operating in hidden corners of nearby space, or if we are seeing the first cracks in our fundamental theories of matter and energy, revealed in the silent impact of a single, universe-spanning particle. Ultra-high-energy cosmic rays push the limits of particle physics, but back within our own solar system, a different kind of gravitational mystery is reshaping our celestial neighborhood. Far beyond the orbit of Neptune, in the frigid, sunless realm known as the scattered disk, a handful of icy worlds are behaving strangely. Their elongated orbits seem to be herded, clustered in a way that suggests the gentle but persistent tug of an unseen shepherd. This is the core of the Planet 9 hypothesis, the idea that a true giant, 5 to 10 times the mass of Earth, orbits our Sun in a distant, slow-motion loop. The story begins with objects like Sedna, a reddish world discovered in 2003. Sedna's orbit is bizarrely detached, a long, skinny ellipse that never brings it closer to the Sun than about 76 times Earth's distance, and swings it out to a staggering 937 times that distance. It takes roughly 11,000 years to complete one lonely journey. Sedna is not alone. Several other extreme trans-Neptunian objects share this peculiar trait, their orbits oddly aligned, as if something massive is holding them in a similar orientation over billions of years. Computer simulations show that the gravitational influence of a single, distant planet could perfectly explain this clustering. This hypothetical world would not be a tiny dwarf planet like Pluto, but a true giant, a super-Earth or a mini-Neptune, a class of planet common around other stars but conspicuously absent from our own inner system. Its proposed orbit is monstrously elliptical, taking perhaps 10 to 20,000 years to complete. At its closest approach, it might still be 200 times farther from the Sun than Earth is, and at its farthest, it could swing out to over 1,200 times that distance, dwelling in near total darkness. The search for this phantom planet is a monumental task. Its incredible distance means it would reflect almost no sunlight, a faint, cold speck moving imperceptibly slowly against the backdrop of stars. Astronomers are using the world's most powerful telescopes, like Subaru in Hawaii, to scan vast swaths of the sky, looking for that one telltale dot of light that moves just a fraction of an arcsecond from one night to the next. The questions raised by Planet 9 are as compelling as the search itself. If it is real, how did it get there? Our standard model of solar system formation does not easily produce a giant planet in such a distant, tilted orbit. Two leading theories emerge. First, it could be a primordial planet that formed much closer to the Sun, only to be violently ejected outward during the solar system's chaotic early days when the giant planets jostled for position. Its orbit was then circularized over eons by the gentle pull of passing stars or the galactic tide. The second, even more dramatic possibility is that Planet 9 is a captured rogue, an orphan planet that was drifting through interstellar space when our young sun's gravity snatched it and pulled it into a permanent, distant dance. Either scenario forces a complete rewrite of our solar system's history, revealing a past far more dynamic and violent than we once believed. Its discovery would do more than just add a new planet to our charts. It would offer a stunning new target for exploration. Imagine a robotic probe launched generations from now on a multi-century journey to rendezvous with this frozen giant. What would we find? A world with a thick hydrogen-helium atmosphere frozen onto its surface, a deep ocean hidden under an ice shell kept warm by radioactive decay in its core. Or a barren, cratered relic, a time capsule from the solar system's birth. Planet 9 represents a profound shift in how we see our home system. We once thought we had a complete inventory, a neat arrangement of planets. Now we must confront the possibility that a major world has been hiding in plain darkness all along, its gravity quietly orchestrating the motions of the outermost ice dwarfs. Its existence would be a humbling reminder that even our own cosmic backyard holds secrets vast enough to rewrite textbooks, waiting for a patient eye to finally bring them into the light. The search for hidden planets and cosmic rays tests our understanding of gravity and motion, but a far more foundational pillar of cosmology is now showing a worrisome crack. This is the Hubble tension, a stubborn and growing discrepancy in one of the most important numbers in the universe, the Hubble constant. This constant is the rate at which the cosmos is expanding, a single figure that tells us how fast galaxies are receding from each other and, by working backward, the age of the universe itself. For decades, astronomers have refined two primary, highly precise methods to pin down this number. but instead of converging on a single answer, they are stubbornly drifting apart, creating one of the most significant crises in modern cosmology. The first method looks back to the very beginning, using the cosmic microwave background, that ancient afterglow of the Big Bang. By meticulously mapping the tiny temperature fluctuations in this background radiation, satellites like Planck can calculate the ingredients of the early universe, its density, its composition, and from that, predict what the expansion rate should be today. This is a top-down approach, starting with the infant cosmos and running the simulation forward 13.8 billion years. The second method builds from the bottom up, using a cosmic distance ladder within the nearby universe. Astronomers rely on pulsating stars called Cepheid variables, whose predictable brightness reveals their distance, to calibrate the distances to galaxies that host a specific type of supernova. These supernova type 1a are the standard candles that allow us to measure distances to faraway galaxies and directly measure how fast they are moving away from us. This is a direct, local measurement of the current expansion. Both methods are exquisitely precise, but they disagree by a significant and undeniable margin. The cosmic microwave background method suggests an expansion rate of about 67 kilometers per second per megaparsec. The local supernova method points to a faster rate, around 73. This is not a small statistical fluke. It is a discrepancy that has persisted and grown with each new, more accurate dataset. It is as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. So what does this mean? The tension suggests that our incredibly successful standard model of cosmology, known as lambda CDM, which includes dark energy and cold dark matter, might be incomplete or subtly wrong. One possibility is that there is unknown physics in the early universe that the Planck data is not accounting for. Perhaps dark energy is not a constant, but evolved or changed strength over cosmic history in a way we have not modeled. Maybe there is an additional, exotic type of neutrino or other relativistic particle that zipped around in the universe's first moments, altering its expansion history. Another, more unsettling idea is that we are not accounting for something fundamental about the vast empty regions between galaxy clusters, that the universe is not as homogeneous as we assume on the largest scales, and this lumpiness is throwing off our measurements. The most mundane explanation, and the one every scientist checks first, is systematic error. Perhaps there is an unseen flaw in how we measure the distances to Cepheid stars, or a subtle bias in the supernova data. Teams are working tirelessly to rule this out, using new data from the James Webb Space Telescope to cross-check the Hubble measurements with unprecedented clarity. Yet, as the measurements become more precise, the gap remains. This is not just an academic headache, it is a direct challenge to our understanding of cosmic evolution. The Hubble constant is the cornerstone for interpreting everything from the age of the oldest stars to the fate of the universe. If we cannot agree on its value, it means there is a fundamental chapter in the story of the cosmos that we have misread. The tension is a beacon pointing toward a potential revolution in physics, waiting just beyond the edge of our current models. Our expanding universe is measured by the ticking of distant clocks, but some of those clocks are running slightly fast or slow. These are pulsars, the universe's most precise natural timekeepers. They are born in the violent supernova explosions of massive stars, leaving behind a rapidly spinning neutron star, a city-sized ball of pure nuclear matter so dense that a single teaspoon would weigh as much as a mountain. If this neutron star has a powerful magnetic field tilted relative to its spin axis, it beams radiation like a cosmic lighthouse. Each time that beam sweeps across Earth, our telescopes detect a pulse of radio waves. For the most stable pulsars, these pulses arrive with a regularity that rivals the best atomic clocks on Earth, ticking with metronomic precision over decades. This incredible predictability makes them perfect tools for an ambitious experiment. Scientists monitor networks of these millisecond pulsars across our galaxy, creating what is known as a pulsar timing array. The idea is to use the galaxy itself as a gravitational wave detector. A gravitational wave, a ripple in the fabric of space-time predicted by Einstein, would subtly stretch and squeeze the distances between Earth and each pulsar as it passes. This would cause the arrival times of the pulses to shift by minuscule amounts, a few tens of nanoseconds over years. By looking for a correlated pattern of early and late pulses across the entire array, astronomers can catch the faint whisper of these waves. Recently, these arrays have begun to hear a murmur, a background hum of low-frequency gravitational waves. The pulses from dozens of pulsars are showing timing anomalies, a common correlated drift that matches the signature of a gravitational wave background. The leading explanation is the combined chorus of countless pairs of supermassive black holes, each binary orbiting each other in the cores of distant galaxies, their immense masses churning space-time as they spiral together over millions of years. This would be the soundtrack to the slow-motion dance of cosmic giants, but the data holds intriguing wrinkles. The strength and pattern of the signal raise questions. Could some of this hum come from something even more exotic? One tantalizing possibility involves cosmic strings, hypothetical defects in space-time from the universe's first moments, thinner than an atom but stretching across the cosmos. As they vibrate and snap, they could produce powerful gravitational waves. Another source might be vast clumps of dark matter, their collective motion generating a subtle, pervasive ripple. Even the possibility of primordial gravitational waves from the rapid inflation of the universe just after the Big Bang is being considered. Each anomalous tick from a distant pulsar is a data point in an experiment testing the very fabric of reality. Are we listening to the expected chorus of black holes, confirming a key piece of cosmic structure? Or is the hum telling us about phenomena we have only theorized, the fingerprints of cosmic strings or the hidden dynamics of the dark universe? Pulsar timing arrays are turning our galaxy into a vast interferometer, one that listens not with lasers and mirrors, but with the patient, precise rhythm of dying stars, each pulse a probe into the deepest forces shaping the cosmos. Even the steady ticking of pulsars cannot be heard from every corner of our galaxy. When astronomers map the Milky Way using radio telescopes, they expect to see a relatively even distribution of these cosmic lighthouses tracing out the spiral arms. But one entire quadrant of our galactic map, a vast pie slice of sky, appears strangely, suspiciously quiet. This is the so-called empty galactic quadrant, a region where the expected chorus of pulsars and other radio sources falls into a profound and puzzling silence. It is not a complete void, but the numbers are off, as if someone turned down the volume on an entire section of the galactic orchestra. The immediate question is why? Is this emptiness real, or is it an illusion created by our own point of view? Our solar system is nestled within the galactic disk, surrounded by swirling clouds of gas and dust that can block certain wavelengths of light. Could a particularly dense, local filament of interstellar smog be lying between us and that quadrant, obscuring our radio view? This is a plausible, mundane explanation, a cosmic curtain drawn across part of the stage. Yet, as surveys become more sensitive and peer through different frequencies, the anomaly persists, suggesting the curtain might be thicker than we thought, or perhaps it is not a curtain at all. This leads to a more profound possibility that the emptiness is genuine. Perhaps the spiral arm structure in that direction is different, less populated with the massive stars that eventually become pulsars. Our maps of the Milky Way are famously difficult to construct because we are inside it, like trying to map a forest from a single tree. We rely on models and inferences. This quiet quadrant could be telling us that one of our spiral arms is less defined or even broken, challenging the perfect pinwheel image we often hold of our home galaxy. But the most intriguing hypothesis points to something invisible shaping what we see. Could the gravitational influence of a vast, clumpy perturbation in the Milky Way's dark matter halo be responsible? Dark matter is thought to form a roughly spherical halo around galaxies, but simulations show it can have substructure, denser lumps and streams. If a particularly massive clump of dark matter exists in that quadrant, its gravity could have subtly influenced the formation of stars billions of years ago, leading to a region less densely populated with the kinds of massive stars that leave behind pulsars. It would be a ghostly fingerprint, a cosmic blank spot created not by absence, but by the invisible hand of dark matter sculpting the visible universe. This quiet sector forces a humbling admission about our place in the cosmos. We have sent probes to the edge of the solar system and gazed at galaxies billions of light years away, yet we still do not have a complete census of our own galactic neighborhood. The structure of our home spiral, the distribution of its stars, and the shape of its dark matter halo remain works in progress. Is the empty quadrant a simple observational gap, a patch of cosmic dust in our eyes? Or is it a clue, a silent signal that the architecture of the Milky Way is stranger and more lopsided than our models predict? Its history written in both the brilliant beacons we see and the unsettling quiet of the places we do not. The universe's first 3 minutes should have left a specific chemical signature, a cosmic birth certificate written in the lightest elements. In that searing heat just after the Big Bang, protons and neutrons fused to form the primordial nuclei of hydrogen, helium, and a tiny trace of lithium. This process, called Big Bang nucleosynthesis, is one of the pillars of cosmology. The calculations are exquisitely precise, predicting how much of each element should have been created based on the known density of the early universe. For hydrogen and helium, the predictions match the observed abundances in the oldest stars almost perfectly. But for the third lightest element, lithium-7, the numbers are catastrophically wrong. The oldest stars in our galaxy, ancient suns that formed from nearly pure primordial gas, show only about 1/3 of the lithium that our theories insist must be there. This is the lithium problem, a stubborn threefold deficit that has persisted for decades, a glaring mismatch between our story of creation and the actual fossils we find in the stellar graveyard. Where did the lithium go, or was it never made in the expected amounts to begin with? Astrophysicists have pursued 3 main paths to solve this puzzle, each one leading to profound implications. The first path looks for an error in our nuclear recipe book. The predictions rely on our understanding of how atomic nuclei interact under extreme conditions, data we derive from Earth-bound particle accelerators. Could there be an unknown nuclear reaction pathway in the early universe, some fleeting resonance or unaccounted-for process that destroyed lithium as quickly as it formed? This would mean our laboratory physics, while incredibly accurate, is missing a piece relevant only to the unique universe-spanning furnace of the Big Bang. The second path looks to the stars themselves. Perhaps the primordial lithium was created in full, but these ancient stars are not the pristine time capsules we thought. Could internal processes like slow-burning nuclear reactions deep in their cores or peculiar mixing patterns in their atmospheres have gradually destroyed the lithium over billions of years? If so, then measuring these stars gives us a corrupted record, like reading a faded parchment where a key line has been scrubbed away. The challenge is that these stars are incredibly stable and simple by stellar standards, making it difficult to find a mechanism that would destroy lithium so efficiently without altering other elements we see in perfect agreement. The third path is the most radical. It suggests the discrepancy is not a mistake in nuclear or stellar physics, but a clue to entirely new physics operating in the universe's first moments. Could exotic particles, like certain types of dark matter, have been present and interacted with the primordial soup, altering the nuclear reactions and suppressing lithium production? This idea connects the microscopic world of particle physics directly to the chemical makeup of the oldest stars in our sky. It proposes that the solution to the lithium problem is not a tweak to existing models, but a window into something fundamentally new, a shadow from the first second of time imprinted on the atmosphere of a 12-billion-year-old star. This tiny deficit of a single element forces a monumental question. Are we misreading the universe's first recipe, misunderstanding the life story of its oldest stars, or being shown the first faint evidence of particles and forces that vanished from the cosmos almost as soon as it began? The lithium problem is a whisper from the dawn of everything, carried to us on the faint light of ancient suns, insisting that even our most successful stories of origin still hold deep and puzzling gaps. That cosmic birth certificate written in lithium is a story of beginnings, but the universe also creates objects that seem to defy the very process of becoming. Drifting through the Coma Cluster, a dense metropolis of galaxies over 300 million light-years away, astronomers found ghosts. These are the ultra-diffuse galaxies, and one of the most famous is Dragonfly 44. From a distance, it has the sheer physical size of our own Milky Way, a vast island of potential. But when you look closer, you see the haunting truth. It contains only about 1% of the stars. Its light is so faint, so wispy, that it was only discovered in 2015 because it was nearly invisible against the blackness of space. Its dim stars scattered like a handful of dust across a football field. These are not small, dwarf galaxies. They are cosmic giants that forgot to shine. The mystery deepens when you measure how these ghostly structures hold together. Using the Keck Observatory, scientists tracked the motions of Dragonfly 44's sparse star clusters. They were whipping around at tremendous speeds, indicating a gravitational grip far stronger than the meager visible stars could provide. The conclusion was staggering. This faint, ethereal galaxy is made almost entirely of dark matter, with a mass nearly 1 trillion times that of our Sun. For every one star you see, there is about 10,000 times more invisible mass holding it all in place. It is a dark matter skeleton wearing the faintest imaginable skin of stars. This presents a monumental puzzle for how galaxies are born. Our standard model says galaxies form when dark matter halos collapse, their gravity pulling in normal gas which then cools, condenses, and ignites into stars. Dragonfly 44 and its kin followed the first step perfectly, gathering an immense halo of dark matter, but then the process stalled. Why did so little gas fall in, or why did that gas refuse to form stars? One leading theory is that these are failed galaxies strangled in their infancy. Perhaps they were born within the harsh environment of a giant cluster like Coma, where the searing heat between galaxies stripped away their gas or kept it too hot to collapse. They were left as dark matter scaffolds, starved of the material needed to build a brilliant city of suns. Another possibility is that they are the stripped remnants of once normal galaxies. A smaller spiral galaxy, venturing too close to the cluster's center, could have had all its stars and gas violently torn away by gravitational tides, leaving behind only its diffuse outer halo and its dark matter heart. Yet, many ultra-diffuse galaxies are found in isolation, far from the violence of clusters, which complicates this story. This suggests they might be a distinct natural class of object, a path the universe can take where dark matter dominates in near total silence. Their existence forces a profound rethink of galaxy evolution. We can no longer assume that a large dark matter halo inevitably leads to a dazzling spiral or a dense elliptical galaxy. The universe has a third, quieter option. These ghosts demonstrate the astonishing diversity of dark matter's influence, showing it can structure space on a galactic scale without ever lighting it up. They are living fossils of a different cosmic history, challenging us to ask if our own Milky Way was ever at risk of becoming such a specter, a vast dominion of darkness punctuated by only the rarest, loneliest points of light. Our galaxy's ghostly giants show dark matter can exist in near silence, but at the very edge of our own solar system, we find a different kind of emptiness, a sudden stop where a bustling cosmic highway should be. This is the Kuiper Belt Cliff. Beyond the orbit of Neptune lies a vast donut-shaped region of frozen debris, the Kuiper Belt, home to Pluto and thousands of other icy worlds. Astronomers expected the population of these objects to gradually taper off as they mapped farther out, a gentle fade into the outer dark. Instead, they found a wall. At a distance of about 50 astronomical units, or 50 times the Earth-Sun distance, the number of detectable Kuiper Belt objects drops off a cliff. It is not a smooth decline, it is a dramatic and unexpected boundary, as if someone drew a line in the cosmic sand and said, nothing beyond this point. This sharp edge defies our basic models of how the solar system formed and settled. The primordial disk of gas and dust that birthed our planets should have scattered material much farther out, leaving a more extended and diffuse population of icy bodies. So what created this sudden frontier? One compelling theory directly ties back to the search for Planet 9. The gravitational influence of a distant, massive planet could have sculpted this edge. As it orbits, its gravity would act like a cosmic shepherd, clearing out a zone and shepherding objects into specific orbital patterns, potentially creating a sharp cutoff at the inner edge of its influence. The Kuiper Belt Cliff could be the calling card of that hidden world, a gravitational signature written in the distribution of icy debris. Another explanation reaches back into the solar system's violent youth, the era of planetary migration. We now believe the giant planets, particularly Jupiter and Saturn, did not form where they are today. They migrated inward and outward, scattering comets and asteroids in a grand gravitational reshuffling. This period of instability could have ejected a tremendous amount of material from the outer disk entirely, flinging it into interstellar space and leaving behind a depleted belt with a sharp outer boundary. The Kuiper Belt Cliff might be the fossilized edge of that ancient clearing event. A third, more dramatic possibility involves an interstellar visitor not of rock but of gravity. Billions of years ago, when our sun was still in its stellar nursery surrounded by other newborn stars, a close pass by a sibling star could have occurred. The gravitational tug from that passing sun would have been like a giant hand reaching into the solar system's outer reaches, stripping away a huge swath of the primordial Kuiper Belt material and leaving behind the truncated belt we see today. Each theory paints a different picture of our solar system's history. Is the cliff a sign of a hidden giant still lurking in the dark, a monument to the chaotic travels of Jupiter and Saturn, or a scar from a close encounter with another star? This mystery at the frontier forces a humbling admission. We have sent probes past Pluto, yet we still do not fully understand the architecture of our own backyard. The Kuiper Belt Cliff is a reminder that the solar system does not just fade away. It ends with a question mark, a boundary that challenges the completeness of our map and whispers of forces, both past and present, that have shaped our home from the shadows. The sharp boundary of our solar system marks the edge of our local chemistry, but when we look beyond, we find a cosmic signature written in a color of light our eyes cannot see. Across the galaxy and in distant nebulae, powerful infrared telescopes detect a set of distinct glowing bands. They are not the clean lines of simple atoms like hydrogen or helium. These are broad, smeared-out emission bands, the kind produced by the vibrations of large, complex molecules. They are chemical fingerprints, clear evidence that something specific is out there, absorbing starlight and re-radiating it in the infrared. The problem is, when scientists compare these cosmic fingerprints to every molecule they can create and study in laboratories on Earth, nothing matches perfectly. These are the unidentified infrared bands, a decades-old puzzle in astrochemistry. The leading suspect for producing these bands is a family of robust, carbon-rich molecules known as polycyclic aromatic hydrocarbons, or PAHs. Picture the molecular structure of soot or the arrangement of atoms in a charcoal briquette. PAHs are flat, stable molecules made of rings of carbon atoms, often with hydrogen atoms attached around the edges. They are tough, capable of surviving the harsh radiation of space, and their vibrational modes should, in theory, produce infrared emission very close to what we observe. But the devil is in the details. The observed bands are slightly shifted or a bit broader than what pure PAH molecules produce in the lab. This suggests the cosmic versions might be slightly different, perhaps larger, charged, or frozen onto tiny dust grains, altering their signature. It is like recognizing a friend's voice on a bad phone line. You are sure it is them, but the static makes you hesitate. So what are these things? If they are indeed vast clouds of complex organic molecules drifting between the stars, their implications are staggering. PAHs and similar large carbon molecules are considered probiotic. They are the intermediate step between simple cosmic gases and the complex chemistry required for life. They are the cosmic Lego bricks, more sophisticated than raw atoms, ready to be assembled into even more interesting structures under the right conditions. This leads to a profound connection. We know that comets and asteroids, the leftover building materials of our solar system, are rich in organic compounds. Missions like Stardust and Rosetta have confirmed this. If these interstellar molecules are the raw feedstock, then the comets that pelted the early Earth could have been delivery trucks, showering our young planet with a rain of probiotic material. The unidentified infrared bands might be the shipping manifest, the spectral evidence of the universe's vast organic supply chain. The mystery pushes our understanding of chemistry to its limits. What exact forms do these carbon molecules take in the extreme cold and vacuum of space? Are they the direct precursors to the nucleotides and amino acids that make up RNA and proteins? Or are they a dead end, a fascinating but inert cosmic soot? Each unidentified band is a question mark in our model of cosmic evolution, a hint that the chemistry of life may not be a rare planetary accident, but a common process written into the very fabric of interstellar clouds, waiting only for a warm, watery world to bring its potential to life. The cosmic dust that writes its signature in infrared light can also gather into vast, opaque clouds, and nowhere is this more dramatically illustrated than with the star that first captured our imagination. Years of relentless observation have transformed the mystery of Tabby's star. The wild speculation about alien megastructures has largely quieted, not because we solved the puzzle, but because the data gently steered us toward a different, yet still deeply strange answer. The crucial clue came from watching how the star dimmed across different colors of light. If a solid object like a planet or a giant solar panel were passing in front of the star, it would block all wavelengths of light equally, creating a uniform shadow. But the detailed observations from telescopes like Spitzer and Hubble showed something else entirely. The dimming was much more pronounced in blue and ultraviolet light than in infrared. This is the classic fingerprint of dust. Tiny particles, smaller than a grain of flour, scatter shorter wavelengths more effectively, letting the longer, redder light pass through more easily. The alien megastructure hypothesis, while thrilling, could not explain this color-dependent dimming. The culprit appears to be ordinary cosmic dust, but its behavior is anything but ordinary. So where did this immense, clumpy cloud of dust come from, and what controls its chaotic dance? The leading theory now points to a catastrophic family event. Perhaps Tabby's star devoured a planet or a swarm of comets, and we are witnessing the aftermath, a vast, uneven debris field of pulverized rock and ice slowly orbiting the star, casting its ragged shadows. Another possibility is that the dust is not from a single cataclysm, but is constantly replenished by the collisions of countless asteroid-like bodies in a densely packed belt, a perpetual demolition derby on a cosmic scale. The irregular patterns of dimming, those deep, asymmetric drops in brightness, could then be explained by the most massive clumps of debris, trailing vast plumes of fine dust in their wake. This star has become a masterclass in cosmic patience. Its long-term light curve, compiled from years of data by professional astronomers and dedicated citizen scientists, reveals another layer of complexity. The star is not just experiencing these deep, random dips. It also shows a slow, secular dimming over the entire period of observation, as if a more uniform, enshrouding haze is gradually accumulating. This suggests we are watching a dynamic process unfold in real time, a star interacting with its environment in a way we have never seen before. While the vision of a Dyson sphere has faded into the background, the lesson of Tabby's star is arguably more valuable. It taught us that nature is capable of producing signals so bizarre they can mimic our wildest science fiction. It underscored the critical importance of long-term monitoring, of watching a single point of light for years to decode its story. And it revealed that the environments around other stars can be far more complex and variable than our own placid solar system, filled with dusty dramas and celestial collisions we are only beginning to comprehend. The star remains an enigma, a reminder that when we find something truly extraordinary, the truth is often stranger than even our most imaginative fiction. Yet even the cosmic microwave background, that ancient afterglow, holds a pattern that makes some cosmologists deeply uneasy. They call it the axis of evil. It is not a malevolent force, but a name born from statistical frustration. When scientists create the most detailed maps of the Big Bang's afterglow, they expect to see a random, isotropic scatter of hot and cold spots like a static-filled television screen. The universe on the largest scales should have no preferred direction, no up or down, but the data whispers something else. There appears to be a curious alignment between the plane of our own solar system, the ecliptic, and certain large-scale features in that ancient light. It is as if the universe's oldest fingerprint is subtly tilted toward our local neighborhood, a correlation that should be astronomically unlikely in a truly random, boundless cosmos. This is more than a minor statistical blip. For the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, it is a potential crack in the foundation. This principle is not just a philosophical stance, it is the bedrock upon which virtually all of modern cosmology is built. It allows us to assume that the laws of physics are the same everywhere and that no place in the universe is special. If that bedrock is shaky, the entire edifice of our cosmic models trembles. So, is the axis of evil real, or is it an illusion? The first and most likely explanation is a subtle systematic error. Perhaps our view is contaminated by something much closer to home. The Milky Way's own foreground emissions, the glow of dust and charged particles in our galactic neighborhood, might be imprinting a pattern that we have not perfectly subtracted from the data. Our solar system's motion through this local medium could create a faint directional signal that mimics an alignment with the cosmic microwave background. Scientists work tirelessly to clean these foregrounds, but the possibility of a residual smudge remains. The second possibility is more provocative, that we are seeing a local violation of isotropy. Maybe the universe is like a vast ocean, mostly uniform, but with gentle, continent-sized waves. Our observable universe, a sphere nearly 100 billion light-years across, might simply be one slightly lopsided region within a far grander and perhaps uneven totality. In this view, the axis of evil is not a flaw in the cosmos, but a feature of our particular cosmic address. A gentle hill in the fabric of space-time that tilts our perspective. The third and most radical interpretation challenges the cosmological principle head-on. What if the universe is not the same in all directions on the very largest scales? What if it has a subtle grain like cosmic wood, with a preferred direction woven into its structure from the beginning? This could point to exotic physics in the infant universe, perhaps a direction to the inflationary field that blew up our cosmos, or the influence of some primordial magnetic field that stretched space-time in a particular way. The axis of evil forces a profound and humbling self-examination. Are we, once again, mistaking a reflection in our own window for a feature of the distant landscape? Or is the universe gently telling us that our place within it is not entirely random, that even the oldest light in the sky carries a faint, enigmatic nod toward the tiny spiral arm we call home? This statistical ghost does not give us answers, it only asks us to question our most basic assumption, that from our tiny vantage point, we can see the universe as it truly is, and not as it appears from one special and possibly skewed location. Even the ordinary matter we are made of hides in plain sight. We have mapped the stars, the galaxies, the planets, yet a cosmic accounting reveals a startling shortfall. From the precise measurements of the Big Bang's afterglow, scientists can calculate exactly how many protons and neutrons, the particles called baryons that make up all normal matter, should exist in the universe today. When they tally up everything they can see, all the stars, galaxies, and the cold gas in between, they come up short by about half. This is the missing baryon problem. We cannot find roughly 50% of the ordinary stuff the universe is supposed to contain. It is not dark matter, it is the very atoms that should be building stars and planets, simply gone from our inventories. The leading suspect for this missing matter is not a hidden dimension or a new particle, but a state of matter so diffuse and energetic it has eluded our telescopes. It is called the warm-hot intergalactic medium, or the WIM. Picture the cosmic web, that vast network of galaxies connected by filaments of dark matter. Theorists believe the missing baryons exist as a superheated, ionized gas, a plasma with a temperature of between 100,000 and 10 million degrees, threading through these invisible filaments. This is not a cloud you could see, it is a ghostly, searing fog filling the spaces between galactic clusters. Proving its existence is a monumental challenge. How do you map a gas so thin that a cubic meter of it might contain only a single atom, yet so hot it glows in X-rays? Astronomers have turned to a clever trick, using distant beacons as backlights. When the light from a brilliant quasar, a galaxy with a voracious black hole at its heart, travels billions of light years to reach us, it passes through these filaments. The superheated gas of the WIM absorbs specific wavelengths of that light, leaving extremely faint absorption lines in the quasar's spectrum, like a chemical fingerprint on a distant fingerprint. Detecting these faint traces requires combining data from multiple space observatories, stitching together ultraviolet and X-ray views to catch the signature of oxygen and other heavy elements that have been stripped of their electrons in the intense heat. Each successful detection is a triumph, a pinprick of light confirming a strand of the web, but mapping the entire structure, understanding its density and how it snakes through the cosmic void, is a task that will occupy generations. This raises profound questions about the flow of the cosmos. The WIM is not a static reservoir, it is a dynamic highway. Simulations show that as galaxies form and cluster, they pull in cool gas from these filaments, fueling new generations of stars. Simultaneously, galactic winds from supernova and black holes blast processed material back out into the web, enriching it with heavier elements. The WIM is the circulatory system of the universe, the medium through which the raw materials for creation and the ashes of destruction endlessly cycle. Solving this mystery is the final step in completing our inventory of the ordinary universe. It asks us to shift our perspective from the brilliant islands of galaxies to the vast, hot oceans that connect them. Finding all the missing baryons would confirm that we truly understand the distribution of everything we are made of, from the atoms in our bodies to the fuel for distant suns. It closes the ledger on normal matter, allowing us to focus entirely on the deeper mysteries of the dark universe that surrounds it. These violent cosmic currents have a source, and some of the most powerful flow from a specific kind of stellar predator. Orbiting silently in the galactic dark are binary systems so destructive they have earned the names of deadly spiders, the Black Widow and Redback pulsars. Here, a rapidly spinning neutron star, a pulsar, is locked in a tight, deadly dance with a smaller, low-mass companion star. The pulsar's intense magnetic field and radiation blast the facing side of its partner with a hurricane of high-energy particles and gamma rays. This relentless assault is literally cooking the companion star, stripping away its outer layers atom by atom and blowing them into space in a superheated wind. Over millions of years, the pulsar is slowly evaporating and consuming the very star it orbits. The process is dramatic and violent, a stellar vampire feeding on its neighbor's lifeblood until nothing may remain but a faint, dead husk or a fully consumed victim. This raises a chilling cosmic question. What is the ultimate fate of these systems? Will the companion star be completely destroyed, leaving the pulsar alone once more? Or does the process reach an equilibrium, leaving a tiny, charred remnant in perpetual torment? Even more puzzling is their origin. How do such extreme binaries form in the first place? A pulsar is born from the supernova explosion of a massive star, a blast violent enough to tear most binary partnerships apart. For these systems to survive, the explosion must have been strangely lopsided, giving the newborn pulsar a powerful kick that somehow kept it bound to its companion rather than blasting it into the void. Alternatively, the pulsar may have captured its victim later, a chance gravitational encounter in a dense star cluster that led to this fatal embrace. These celestial predators are more than just cosmic curiosities. They are unparalleled natural laboratories. By observing them, we can study high-energy physics in conditions we could never replicate on Earth, watching how matter behaves under the influence of a magnetic field trillions of times stronger than our planet's. We witness real-time mass transfer, a fundamental process that shapes the lives of many binary stars, but here pushed to its most extreme and terminal limit. And we get a front-row seat to the long-term evolution of compact stellar remnants, the dense corpses of dead stars as they interact with and ultimately destroy their surroundings. Each pulse of radiation from the spinning neutron star is a beacon from this ongoing annihilation, a clock ticking down the lifespan of a star, teaching us about the forces that can both create and unravel the universe's most intense relationships. Deep within the heart of our own galaxy, a silent, invisible storm is raging. For over a decade, the Fermi Gamma Ray Space Telescope has been mapping the sky in the most energetic form of light, and its data revealed something startling about the Milky Way's core. There is a massive, unexplained glow of gamma-ray radiation, a diffuse excess that balloons outward from the galactic center. It is not coming from any single, brilliant source we can point to. Instead, it is a pervasive fog of high-energy light that should not be there in such abundance, according to our standard models of what populates the galactic core. This is the galactic center excess, and it is one of the most tantalizing dark matter hints we have ever seen. The reason for the excitement lies in a compelling theory. Many models of dark matter, particularly those involving weakly interacting massive particles, predict that these particles could be their own antimatter counterparts. If that is true, then wherever dark matter is dense enough, two particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a spray of gamma rays. The center of our galaxy is thought to be the densest region of dark matter in the entire Milky Way, a perfect place for such rare annihilations to occur at a detectable rate. The shape and spectrum of the excess glow match some of these theoretical predictions eerily well. It looks for all the world like the funeral pyre of invisible particles. But the universe is rarely so straightforward. A chorus of astrophysicists points to more mundane yet still fascinating possibilities. the glow could be coming from a vast, unseen population of millisecond pulsars, the rapidly spinning corpses of dead stars. Thousands of these faint, ticking lighthouses, each too dim to see individually from our distance, could collectively produce exactly this kind of diffuse gamma-ray haze. Our galaxy's core is a crowded place, and we simply may not have the resolution to pick them all out from the brilliant background. Another candidate is the sleeping giant at the very center, the supermassive black hole Sagittarius, a star. While it is quiet now, it may have been explosively active in the relatively recent past, perhaps just a few million years ago. A past outburst could have accelerated particles to immense speeds, creating a bubble of high-energy radiation that is still fading today, like the afterglow of a cosmic flashbulb. So we are left with a critical, high-stakes debate. Is the galactic center excess the first indirect glimpse of dark matter, the signature of the universe's most elusive substance finally revealing itself through its own destruction? Or is it a complex astrophysical puzzle, a testament to the violent and crowded history of our galaxy's chaotic heart? The answer will not come easily. Distinguishing between a smooth dark matter signal and the lumpy glow of countless pulsars requires exquisitely detailed new maps, possibly from next-generation gamma-ray telescopes. But the implications are monumental. If this is dark matter, it would be a revolutionary moment, confirming not only the particle nature of this mysterious substance, but also giving us crucial clues about its mass and how it interacts. We would move from mapping dark matter's gravity to studying its chemistry, opening an entirely new window into the hidden majority of the cosmos. The silent storm at the center of our home galaxy is either a message from the dark universe or a reminder that even our own backyard still holds spectacular secrets. Our galaxy's violent core is a place of extremes, but high above the galactic plane, a quieter, older mystery drifts through the halo. NGC 6791 is not just another ancient star cluster. It is a cosmic paradox that has rewritten the rules we thought governed stellar retirement homes. Most globular clusters are pristine relics from the galaxy's infancy, vast balls of hundreds of thousands of stars that all formed together from a single cloud of primordial gas. Because they formed so early, before generations of supernova had seeded space with heavy elements, their stars are metal-poor, containing only trace amounts of anything heavier than hydrogen and helium. They are the galaxy's fossils, simple and pure, and NGC 6791 shatters that expectation. It is incredibly old, roughly 8 billion years, placing its birth in the galaxy's chaotic youth. Yet when astronomers analyze its light, they find a stunning abundance of iron and other metals. Its stars are about twice as rich in these heavy elements as our own Sun, which is a relative youngster. This combination, great age and high metallicity, should be impossible. It is like finding a perfectly preserved medieval manuscript written on modern, laminated paper. So how did this cluster become so enriched? The first possibility is that it did not form in the pristine galactic halo at all, but was born in the metal-rich chaos of the galactic disk, the crowded central plane where star formation and supernova explosions were already recycling heavy elements. Perhaps it was violently ejected from the disk by a gravitational encounter, flung high into the halo where it orbits today. This would make it an immigrant, not a native of the halo, carrying the chemical signature of its more industrious birthplace. The second, more complex idea involves a dramatic later chapter. Could NGC 6791 have been born as two separate clusters that later merged? One cluster, old and metal-poor, could have collided and combined with a younger, metal-rich cluster, creating a single, chemically confused family. The stars would now be thoroughly mixed, their orbits scrambled, presenting us with an average metallicity that defies a simple history. There is even a third, speculative notion that this cluster formed in the aftermath of a uniquely catastrophic event, like the collision of two gas-rich dwarf galaxies, creating a single, intense burst of star formation from material that had already been heavily polluted by earlier generations of stars. The existence of this strange cluster forces a profound rethink of the early galaxy's environment. It tells us that the conditions for star formation were not uniform even in those distant times. Pockets of enriched gas must have existed alongside pristine clouds, meaning the first generations of stars lived, died, and recycled their material back into the cosmos with startling speed and efficiency in some regions. NGC 6791 stands as a chemical fossil from a lost era, a testament that the galaxy's youth was not a single, simple story of gradual enrichment, but a tapestry of diverse, isolated events. Its very presence asks us to question how many other anomalous clusters might be hiding in plain sight, their quiet light holding stories of mergers, migrations, and cosmic disasters that we are only beginning to decode. Even the galaxy's most monstrous anchors can be torn from their foundations. At the heart of nearly every large galaxy, including our own, sits a supermassive black hole, a gravitational titan millions to billions of times the mass of our Sun. We think of them as immovable fixtures, the silent engines around which entire galaxies slowly spin, but the universe has a way of proving our assumptions incomplete. Through the ripples in space-time known as gravitational waves, we now understand that when galaxies collide, their central black holes will eventually spiral together and merge. Einstein's equations predict that this final, violent union is not perfectly symmetrical. If the two black holes have different masses or spins, the merger can launch the newborn, more massive black hole out of the galactic core at incredible speed, like the recoil from a cosmic cannon. These are the runaway supermassive black holes, theoretical ghosts that may now be stepping into the light of observation. Astronomers hunt for these renegades by looking for the telltale signs of a displaced monster. One promising candidate is a quasar known as 3C186, a brilliant beacon of light powered by a black hole feasting on gas. The strange thing is its location. It is not at the heart of its host galaxy, but offset by about 35,000 light-years, and it is moving away from the galactic center at a staggering speed of nearly 5 million miles per hour. The most plausible explanation is that we are witnessing a black hole in the act of being ejected, still shining brightly because it managed to bring a cloak of gas with it on its escape, fuel that continues to feed its brilliance as it flees. Another clue comes from galaxies that appear to have no central black hole at all, or ones with a displaced cluster of stars marking the path of a recent violent departure. The existence of these cosmic cannonballs forces us to confront dramatic questions about the life cycle of galaxies. How common are these events? In a universe built on collisions and mergers, they may be a regular, if spectacular, feature of galactic evolution. Every major merger could potentially end with a recoil, though the speed and trajectory depend on the precise dance of the two black holes. The fate of the galaxy left behind is equally fascinating. With its central gravitational anchor suddenly gone, the stellar core of the galaxy could become unbound, slowly puffing out into a more diffuse shape over billions of years. The loss of the black hole might also shut down future episodes of brilliant quasar activity, fundamentally altering the galaxy's development. But what of the black hole itself, hurtling through the intergalactic void? Can it shine? The answer depends on whether it can find new fuel. In the sparse deserts between galaxies, gas is exceedingly thin. A runaway black hole that did not bring a sufficient gas supply with it would quickly become dark and invisible, a true ghost wandering the cosmic dark. However, if it travels through a filament of the warm, hot intergalactic medium or plows into a cloud of stray gas, it could ignite once more, becoming a nomadic quasar with no galactic home, a lone beacon shining in the emptiness. This possibility paints a haunting picture of the universe's most destructive objects cast adrift, capable of flaring back to life in the most unexpected places. These events are the ultimate test of our understanding of extreme gravity, providing a natural laboratory for the physics of black hole mergers and recoil that we could never simulate on Earth. They reveal a universe that is not static but dynamic and violently creative, where even the mightiest structures are not permanent, and the forces that shape galaxies can, in an instant, expel their very hearts into the endless night. Even the grand escape of supermassive black holes may be part of a larger, more mysterious current. For over a decade, astronomers have tracked the subtle motions of entire galaxy clusters, not just their expansion away from us, but their drift across the sky. What they found is deeply controversial, a phenomenon called the dark flow. These immense clusters, each containing thousands of galaxies, appear to be streaming in a common direction at speeds of nearly 2 million miles per hour. This is not the uniform expansion driven by dark energy. This is a coordinated drift, as if a vast, unseen river is pulling them all toward a single point on the cosmic horizon, far beyond the edge of our observable universe. The most startling implication is that this motion cannot be explained by any known mass within our cosmic bubble. The gravitational pull required to create such a coherent flow would have to come from something truly colossal, a structure of unimaginable scale that lies so far away its light has not had time to reach us in the 13.8 billion years since the Big Bang. This is not just a hidden galaxy or a cluster, it would be a supercluster, a titanic concentration of mass residing in a region of space that is, for now, forever beyond our view. The very idea challenges a fundamental tenet of cosmology, the cosmological principle, which states that on the largest scales, the universe should look roughly the same in all directions and have no preferred center. The dark flow suggests a profound lopsidedness, a cosmic tilt that points to an external gravitational anchor. Naturally, such a radical claim has met with intense skepticism. Critics argue it could be a systematic error, a subtle miscalibration in how we subtract the motion of our own solar system or account for the microwave background. Others suggest it might be a statistical fluke, a chance alignment in the motions of the studied clusters that disappears when you look at a larger sample. The debate has raged in journals and conferences, with newer analyses sometimes supporting the signal and sometimes dismissing it, keeping the mystery alive but unresolved. If the dark flow is real, its implications are staggering. It would mean our observable universe, a sphere nearly 100 billion light-years across, is not the entirety of existence. It is merely a local neighborhood, a single bubble in a far vaster cosmos that extends well beyond our event horizon. The structure pulling on us could be a remnant of the chaotic era before the Big Bang, a scar from when our universe was born in a much larger multiverse. Or it could be evidence of a cosmic collision, our universe brushing up against a neighboring one in an infinite, frothing sea of realities. This is not just a map of where we are going, it is a potential window into what lies outside our cosmic home. The dark flow asks the ultimate question about scale. Are we living in a finite, observable domain, or is our entire reality just one island in an endless archipelago of universes, each with its own laws and history? The answer, if it ever comes, will not just add a new chapter to cosmology. It will rewrite the preface, suggesting that everything we have ever observed is merely the local weather in a climate we have only just begun to suspect. This cosmic flow of galaxies might hint at a universe beyond our own, but one ancient star within our own galaxy seemed to directly challenge the universe's very birth date. It is called the Methuselah star, officially catalogued as HD 140283, a faint, fast-moving sun in the constellation Libra. When astronomers first measured its properties using the Hubble Space Telescope over a decade ago, they received a profound shock. Their initial calculations suggested an age of approximately 16 billion years. This was a number that broke cosmology, for the universe itself, as measured by the cosmic microwave background, is only 13.8 billion years old. A star cannot be older than the cosmos that contains it. This impossible age was not a sign of faulty physics, but a call for better measurements. The key to dating a star like this lies in its composition and its distance. Methuselah is a subgiant, a star that has exhausted the hydrogen fuel in its core and is beginning to transition into a red giant. Its brilliance and temperature place it at a very specific, short-lived stage of stellar evolution, allowing for a precise age estimate. But that estimate depends critically on knowing exactly how far away it is and how much metal it contains. The star is incredibly metal-poor, meaning it has only a tiny fraction of the heavy elements like iron that our Sun possesses. This purity marks it as a second-generation star, formed from the ashes of the very first stellar explosions in the cosmos. To solve the paradox, scientists refined both numbers. More precise parallax measurements from the Gaia spacecraft nailed down its distance at just over 190 light-years. Simultaneously, sophisticated spectroscopic analysis fine-tuned the measurements of its oxygen and iron content. These crucial updates fed into the stellar models, bringing the star's estimated age down. The current best estimate places Methuselah at about 14.5 billion years old, give or take 800 million years. This new age is just within the margin of error of the universe's age, resolving the direct contradiction but leaving a profound mystery intact. This star remains staggeringly ancient, arguably the oldest known individual star whose age we can measure. It is a relic from a time when the galaxy was just assembling itself from primordial gas. The questions it raises are fundamental. How did such a star form so quickly after the Big Bang? The first generation of stars, called Population 3, would have been monstrous, short-lived behemoths made of pure hydrogen and helium. Their supernova explosions would have seeded the surrounding clouds with the first sprinkling of metals. Methuselah, with its minute but detectable metal content, must have been among the very first stars to form from that newly enriched material. Its existence tells us that the transition from the first stars to the second generation happened with breathtaking speed, perhaps within just 100 million years. This star acts as a crucial benchmark, a cosmic clock set in the earliest days. Its precise age helps astronomers constrain the timeline of the Big Bang itself, placing limits on how fast the first structures condensed out of the cooling universe. If our models can account for the formation of a star like Methuselah so early, they are likely on the right track. If not, they need revision. This faint point of light is more than an ancient curiosity. It is a living witness to the dawn of time, a single survivor from an era when the night sky was a new and startling invention. Its light a direct message from the moment the cosmos first learned how to build a sun that could last. These 30 cosmic discoveries are not a checklist of solved problems, but a map of the unknown. Each one, from the silent scream of the wow signal to the phantom pull of the great attractor, follows the same pattern, a profound revelation that does not close a door, but opens a hallway lined with new, even more perplexing doors. This is the true nature of cosmic exploration, a process where every answer is simply a better, sharper question. We do not eliminate mysteries, we refine them, trading simple puzzles for profound enigmas that push at the very boundaries of physics and force us to question our most fundamental assumptions about reality, from the nature of gravity to the ultimate fate of everything. This relentless cycle of question and deeper question is not just academic, it is the engine of our future. The quest to understand dark energy is not merely about charting the universe's end. It is a search into the fabric of empty space itself, an investigation that could one day reveal new principles of energy we cannot yet conceive. Wrestling with the Fermi paradox does more than ponder alien life. It forces us to define what a sustainable, enduring civilization looks like, shaping our vision of a potential galactic society and our own survival. Cataloging exoplanets in habitable zones is the first step in a practical interstellar ambition, turning star charts into future destination guides for generations we will never meet. Every unexplained radio burst, every ghostly galaxy of dark matter, every ancient star older than it should be, these are not failures of understanding. They are invitations. They are the universe's way of showing us where the next frontier lies, the puzzles that will drive the telescopes, the space missions, and the brilliant minds of the next century. So the next time you look up at the night sky, remember you are not looking at a static picture. You are gazing into a living, breathing conversation, a story still being written where the most exciting chapters are those we have not yet imagined. Stay curious, because the greatest discovery is never the last one. It is always the next one, waiting just beyond the edge of our current